doing this, should be smaller than the pore size of the material. Okay, and secondly, what happens is that they must be in order to get adhere to the walls of the pores, so they must be transported. So they must be transported, to the walls of the pores, or the chance of them hitting the pores should be high. Okay. And third is that they should have uh, you know they should have an affinity to attach. So they should have an affinity to attach with our pore surface. Now, if the surface is not conducive for the attachment, it won't get attached. Okay, so they will pass right through this pores, and they will not get it. No, so you can understand that all our particles are if they are hydrophobic in nature, and our porous materials are hydrophobic, so there will be an affinity for this hydrophobic material, and so you can see that pore blocking can be a significant phenomenon when we have hydrophobic membrane versus hydrophilic membrane. Hydrophilic membranes won't have lot of pore blocking, rather than hydrophobic membranes. So you have to consider whether hydrophobic versus hydrophilic nature of the particles that we are talking, as well as the nature of the membranes that we are talking. Okay. Now see that the third way is is to formation of the cake layer. So cake layer formation is also something which is good in the sense unless the cake layer sometimes acts like a secondary filtration layer, right? Why? Because if the cake is formed, then obviously they will add to your porous nature, or will block all the other particles that will directly pass through this cake. So it actually adds to filtration, but at the same time it is not actually good for our filtration membranes, because they get choked. Okay. So and these materials, they are actually size is greater than the size initially. The materials which are there on the surface, they're greater than the pore size. Okay. So they should be greater than the pore size of the material. And when they are deposited here, they will offer more resistance or less amount of path for other smaller particles to pass through, and basically what you have that you end up removing particles much smaller than the pore size of the membrane. Now this thick layer acts like a dynamic, I would also say dynamic filter, because when you clean your filter, then obviously they they can be removed, and also when you start filtration, they come back again to form the fouling layer. So these are the three types of mechanisms for which the fouling takes place. Now we also have to understand. We talked about how to remove the fouling. Okay. So reversibility of fouling is something which is very important. Okay? Now, fouling can be irreversible or reversible. Now, what happens is that sometimes the particles, suppose here these are small particles which got absorbed to the surface. Now, if something gets absorbed on the surface, then obviously, it is not just the position of the particle on the surfaces. They are just like, you have all this material, absorbed on the surface, which is, some other type of force. Now, if you pass, water like a backwash will clean out your, particle docking the force or maybe take there. But what happens to this is that, you cannot really make backwash and clean out those particles which are retained due to other type of interaction like hydrophobic interaction or interaction like this. So there will be a permanent loss of weight, when or permanent flux loss when you have this kind of stuff. So now this is another. So in a previous class we saw a particular way of learning our filtration membranes. And we said that if it touches a point or it reaches a maximum level of pressure, it should be cleaned chemically. So let us also see what happens for a particular or for a real life scenario. So this is on the y-axis we have specific flux, and we know this is known as JSP. So specific flux at any temperature here is called JSP, and so we are writing specific flux here, and we are trying to see time on volume of water filter. So now you can see here that this is the new membrane, and when you do this, this is the point where you need to have a backwash. You do the backwashing the initial start point, it declines, saying that there will be chemical, there will be deposition of particles within the bed which cannot be cleaned by normal hydrodynamic forces which are provided during backwash. Now in this point you need to have a chemical fouling. So this chemical fouling, so we have irreversible fouling and reversible fouling, and one part of this chemical fouling is reversible. So we use some of those chemicals which actually reduces or changes the dielectric constant within the membrane, which actually when we go about learning about absorption, we will see that there are other things that we can do. We can actually, absorption also depends on the weightability of the surfaces, as well as on the electrical interaction between the particle and the membrane layer, as well as on the dielectric constant of the medium we use. Okay, so dielectric constant is nothing but it tells us about how the electric charges can be, the potential electric field can be transmitted between the particles. Now, obviously, for those where you can reverse this particular phenomena, using maybe detergent or maybe somehow kind of a solvent, those are effective. But even after death, they will not be come back to this original state. So this is called irreversible fouling. So you can see this is the original state here. So this is the top line is the original state, and then when you do the chemical cleaning, then this part which can be restored is known as chemically reversible. So this is actually the chemically reversible fouling, and the part which cannot be restored, which is called chemically or irreversible fouling or permanent loss of the flux. So this is how we can think about the resistance in our membranes. Now, okay, so let us have one example on the resistance calculation of let us not get this enough about fouling. So fouling, one way is that we can, there are a lot of ways that we can model the fouling, but one particular thing that we practice in the industry is called membrane fouling index. So there are different models that tries to define the fouling of the membrane. Somebody thought that, well, if I look at the membrane, the fouling can be, so the fouling are taking place in different ways. What are the different ways? That we have already discussed that, say, let's say pore blocking, okay, or pore constriction, okay, or chemical nature. So we can actually imagine that there are this fouling is like a resistance taking place within the membrane, okay, and these resistances are in series, and this is one way of modeling this. So all the fouling are like resistances, and maybe hydraulic resistances, and they are in series. Resistances in series. So this is one model, resistances in series model, where different types of resistances may be there, corresponding to hydraulically reversible. So one type is hydraulically reversible or backwashable fouling. And there will be another type of fouling which is chemically reversible. And there may be irreversible fouling. There may be cake layer fouling, cake layer resistance. Okay, so all these things are modeled as and then maybe pore constriction resistance. So there might be all number of resistances that we can think about, and can think that they are all different resistances, just as you see in your electric lines, and then we can say these are in series, and we can have this model. But if there are lots of ifs and buts and doubts in this model, because there are no particular thing, because if you see, the model can also, there will be also biofouling, which is very different from the way that we see. Biofouling may, the, the bacteria, they can grow over time, so it's not a dynamic thing. So we have a natural organic matter fouling. So there are different types of other variations, that also comes when we talk about fouling. Now, so there is no particular thing that we can actually, particular model that we can actually point out to. So that is why people have have developed something called a fouling index. Okay, so and this is based on the resistance in series type of thing, and but it doesn't include all these types of variations. It simply says there are two resistances. So it simply says there are two resistances. One is for clean membrane. Obviously, this is because of the membrane porosity and everything, and the other is resistance due to the fouling. So these are two resistances, for the water to pass through. And if you recall, when we discussed last time, we said K equals to P by mu into Km, right? So if you recall what I said, K equals to delta P mu by Km. Here, what I will say, I'll add another resistance right here. So Km is the resistance due to membrane. So Km, resistance due to clean membrane. Now we will add another term here, which is fouling resistance. So Kf is fouling resistance. Okay, so these are the two resistances, and all of them are having units of per meter. Now Kf also, as you can understand, that the membrane, just looking at this figure, when suppose you have, you try to look at the figure, in this direction. Okay. So what is this? Initially, the membrane surface might look like this, and as you, before, when you start your membrane after backwashing, the membrane would look like this. Okay, the last figure, and then when you after some time, this will look like this, and then like this, and then like this. So this is completely fouled membrane. So you can see that the resistance is developed over a period of time, depending on how much of water that you pass through this. If you look at this graph also, you see the resistances develop over time. So specific flux actually decreases over time, and at point of time we realize that we are backwash. So that means this cake formation or this KF value is not kind of same, is not a constant. It is related with value of K and let's say V into SP. Where K is the rate of, we say that K is the rate of increase in resistance to pass more and more water. So this is called specific throughput. Okay. So this is nothing but what is the loading rate on the membrane. So this is volume of water passed, filtered per unit membrane. So you can understand that this is unit is how much? Meter cube per meter square. Okay. So this is the unit, and this one has a unit of, let's say, meter minus 1, okay, per unit, okay, and so it has a unit of meter minus 2. Okay. So this is how we can define the kf over the amount of filtration done. Okay. So with this, and we also knew that specific flux is nothing but J flux at any time divided by delta V. Okay. And this is equals to, then we can write K then plus Kf. Alright. And so that we can write 1 over mu
ये मोर बेबी सब हां मोर टिकट का जाते हैं 150 तक कल कितना पाए हैं टोटल
for a new membrane.
बहुत रुपए के लिए तो मैं ऐसे थे चिकन की तो वो सुड़ा दे बस नहीं
PSP was
नहीं
right. And so second term becomes
नहीं तकल कितना
or let me write Kf equals to 0. So
अबे
then
150 वाट का तो
Ks
ठीक है
1 by.
और कल क्या कितने रहे
So this is the key loss, and typically
आउट साउंड
what
में
happens is that
250 रुपए कल एक लाख वाला बुद्धि है जो इस जगह में सिखावा
we can actually write
हाँ तो 200 तो बचे ना जो एक 350 तो 150 पहले 200 नहीं थे 200 मिलता
if we divide
तो 200
this
मिलता है
base.
इसके भी बने थे तो कुछ ठीक
So
है
this is the right? So now we get it lost. So if we do this by JS, this is nothing
अरे यार
but
मुझे वीडियो रहा थी हमारी कुछ जगह थी वीडियो नहीं है
equations. This is nothing but Km over Km plus K. Okay, and this is the normalizing agent. So we can say normalized discrete flux. And this is known as, let's say, if I write JSP dash. Okay. And fouling index, membrane fouling index is known as K over Km. Okay. So K is the fouling at any particular or any particular state of holding your filtration ground, and Km is so this is membrane fouling index, and this is how it is defined. So it can, now you can see that if I write here, we can very well understand. So from JSP dash and this, what I can write is that 1 over JSP dash equals to 1 plus NFI into JSP. Just have a look at this equation. so that it comes from this equation from this if I write this equation. Okay. Now that means this is you can see this is y plus y equals to mx plus c. So this is nothing but y equals to mx plus c. While m equals to the method for the inputs. So if you try to plot the value of 1 over JSP dash, okay, over VSP, and then you get a straight line, for which the slope of this line is slope is your m5. Member Fouling index. So it's a empirical fouling index, and it can be used to compare the rate of fouling between two different types of testing. Like you have done a bench scale and a pilot scale result. So so this is how we can do it. Obviously, the water quality for both the cases should be the same, and immunifying has been used to compare fouling between different membrane products and different source waters. Okay, and it shows that if we calculate the NFI values, then our bench scale and pilot scale data, they actually match each other. Now, we will I will give you certain tutorial sheets where you can actually use this and try to find out the NFI value for a certain case. And maybe after when you solve this, I will be along with you so that you can solve this. Now, regarding the use of filters, microphone filters in real life, let me show you one particular. So before that, let me show from here. So this is a figure showing the result of experiment for the rate of fouling of 0.22 micron quantification membrane used to treat the dilute biomass solutions. And so you can see here that these membranes are used in different flux level, and this is the transcranial pressure that we are calculating. And when it reaches a particular value, then we will try to stop the membrane run and try to regenerate the membrane. Okay. Now look at the first one. It is running at 50 liter per meter square hour. So you can understand that from the MA5, you can say that value, VSP value is kind of a, it defines if you pass more flow to the membrane, then obviously your membrane is getting choked, over time, right? So now you can see here that if we run at a very high flux, obviously within a small time we are trying to choke our membrane very quickly, and you can see that the flux rises, the transmembrane pressure rises very quickly, and it rises to only a certain point where we need to stop the membrane and go for backwards. And as we decrease the flux to the membrane, you can see that your transmembrane pressure does not rise that significantly. Now, what does it tell us? That for different membranes, also depending on the different source water, we have to find out an optimum flux value in which the membrane would not get into lot of into a very high or frequent choking of the membrane. So in this case, probably 30 liter per meter square hour is the best way to go. But again, here is the problem that so this is 30 liter flow rate, 30 liter per hour per meter square of membrane. So per meter square of membrane. So for let's say we have 3000 liter per hour is our total flow. Now, how much membrane area we will require? So, membrane area required, that's like A surface. So, in this case, membrane surface area requirement will be 100 meters square. Okay. Now, obviously, to produce this amount of water, you need to have 100 meters square of membrane, which also will be the membrane cost depends on how much square meter of surface that you require. Okay. So now consider this with this one. Then obviously 3000 divided by 40. So that is your membrane area requirement, and this will be 75 meters square. And in this case, there will be 60 meters square of membrane area. So you can see that our capital investment for these three cases are different, but again, in these cases, the operation will be easier and smoother, and you will not have lot of disruptions during the operation. Okay, so this is one way we can optimize our membrane surface area versus. So there will be a trade-off between membrane surface area requirement as well as the fouling of the membrane. Now, so there are other ways that we can also try to do is that we can produce a pre-filter membrane ahead of your final membrane. So this is you can see this is the 0.2 micron nominal size filtration final membrane cartridge filter. So this is our filter, and inside this filter housing there is a membrane, okay, of 0.2 micron size. Now what happens is that if we do not have no pre-filter, so this initial filter is not there, then you can see that immediately the pressure rises, and then there is a need to backwash. Okay. Now if you put a pre-filter here. Okay. So you put a pre-filter so that first the water gets into this. Then there is a initial level of filtration, and then it goes to the membrane here, which is the final step. And so you remove 0.2 micron, and below size of size is above 0.2 micron, or 0.2 micron size is 100% removed in this membrane. So and then you get the final filtering here. Now what will happen? This pre-filter will also have a role to play. You can see that if the pre-filter is too coarse, that means the size is too big, let's say 10 micron size filter. Okay, so it doesn't have much effect on your filtration rate. Now your combined filter will have this much of pressure, total pressure requirement will be like the farm line. Now you can argue that the final filter is this one, and this is the pre-filter. Of course, this is better than this situation is better than this situation, but again, so that see that obviously there is some there is way to it can be much better. Okay? So if you put the pre-filter here, which is fine, that means you have, let's say, 1 micron of this thing. So your final filter will have a very, pre-filter will have will choke first than your final filter. So this is your final filter. In this case, the pre-filter will choke faster than your final filter, and your combined curve is actually governed by the pre-filter filter. So you need to actually make the trial and error, and probably if you choose somewhere between 5 micron, obviously it depends on your inlet water characteristics, and then both these filters will have similar type of fouling propensity. Then you can see that this is the better situation. So you can optimize the pre-filter and you can have a better situation. Obviously this situation is not better. Okay. So this is about microfiltration index. Just to tell you about one of those industrial uses, biggest industrial uses. We have uses in wastewater. Okay, wastewater. We are having uses in water treatment, and this is a typical example in pharma industry. Okay, pharmaceutical industry, and how do we do this? You see that wastewater. I think probably you have heard about or you know about the activated sludge process. Okay, so in activated sludge process, what we do, we try to grow our bacteria right here, and then we try to filter this. We try to settle the bacteria and then recycle our bacteria back into the process, and a part of the bacteria is removed here, and we get the treated water. So from right here. Okay. Now in the process is like my membrane bioreactor. What we do? We use this, and in place of this sedimentation tank, we use microfilters. Okay, so microfiltration devices are used, and we get treated water, right through this here. So this is your treated water, this is your membrane, and here you actually concentrate the bacteria, you remove the bacteria, and some of the bacteria is put back into the processing. So this is your MBR, or membrane bioreactor. So membrane bioreactor is one of those processes where you can actually remove those bacteria from your treated wastewater. Now obviously in water treatment we use it for disinfection purpose. You pass your stuff through a bank of filters, and the microfiltration is one of them, and you take the treated water. It removes all the bacteria, but it cannot remove virus and everything. Virus and smaller size molecules. So you have to provide, if you want to remove virus, you have to provide another filter afterwards. Which is, so we have microfiltration, and then next you have to provide an ultrafiltration membrane right here so that it is completely disinfected. Okay. Now in pharmaceutical industry, if you see, I have provided a flow diagram here. This is a typical diagram for producing injection quality of water or sterile water. So you have taken the corona vaccine, and it was like, or any vaccine or any injection that you take, or maybe some intravenous fluid, it should be free from any kind of bacterial contamination, right? So we have a different ways of doing this. So it goes through the water that is used for ampules. It goes through different levels of screening and everything, and then of course you have at different levels you have filtration and stuff, and then but at the end, before you put this into the ampules, so you can see all these processes are there. You have reverse osmosis, ion exchange, resin based methods, lift filtration, and then again you get back to, you can condense it at 80 degrees centigrade, and then you use air to this is all within the process, but you can see here at the end of the process we have 0.2 micron filters. 0.2 micron filters are effective in removing the bacteria, and it goes into the filling system where ampules are filled with with this water, or maybe intravascular or IV fluid is filled with this water, and this is so this is how microfiltration membranes are used, and what are the fouling characteristics and everything that about microfiltration membranes. So I will take another day to complete the ultrafiltration process, which will be on Wednesday, and on Friday we'll move over to the membrane-based filtration, which is reverse osmosis and nanofiltration. Now, before I close today, so this is for ultrafiltration. We'll talk about this in the next part. So this is about ultrafiltration. If you have noticed that I have uploaded, two sets of documents. One is your tutorial sheet for whatever we have discussed from sedimentation, flocculation, coagulation, filtration, and I have compiled from some book, some chapter readings about those. But again, I should tell you that you should have consulted your reference books, and should be knowing more about what I am teaching in the class. More than that, you should have gathered information. Otherwise, the learning is not complete. So take the help of the reference material that I have uploaded on the Git page, and try to solve those tutorial questions, and ask me if you have problems in solving those tutorial problems. So as it is my policy not to ask for a submission for your all those tutorial problems, but of course you can. I encourage that you try to discuss the problems within your group and come back to me on the collaborative solving does not solve the problem. Okay. So, but you can always ask me question on if you have problem on the tutorial sheet. So please try to solve those tutorial sheets, because very soon we will have a quiz on what we have already discussed. Regarding the day of the quiz, there is no date on the quiz. All of a sudden you might have a quiz given to you within a class. So be prepared for those things and be regular on those things. Okay. So thank you for being with me. Today I feel a blunder, not sending you the invitation properly, but I promise that I will start the training. Alright? Sir? Yes?
Sir, there are some programs which help like exact answer.
Just give me a minute. Just give me a minute, please. Let me ramp up the word.
Yes, sir, there are problems which have exact answer. Like in the tutorial, it would be really helpful if you could share answers of those problems with us.
Okay. So you are giving me a big task. Actually, then I have to solve all those problems and again come back with the answers. Is it good to tax me?
No, sir, I'm not saying like whole design problem, everyone's answer will vary, but for like questions like in first question we have to calculate TDL and in
Okay.
such type of problem.
I mean, I understand your whatever you're saying. I'm not saying that you don't have to submit. If you want, you may solve it and either email your solution to me. I'll go through them, and if there is any problem in your solution, I'll definitely check them out, and I will let you know if it requires any modification. Or otherwise, you are free to send me. That's what I said. I'm not saying that you don't send me your solutions. Please send me those if you are done. But what I'm trying to say is that I'm not actually the marks will not be given on this. Whether you are solving your tutorial or not, because from my previous experience, what I see that when I ask you to solve those tutorials and submit it to me, so in many cases I see there has been mass copying. Okay. So if it is a mass copying, then the real purpose of giving you this is really defeated. Okay. And on top of this, I am bombarded with a lot of copied stuff. Okay. So it is better that you try to solve it, and if you are sincere and if you come back to me, sir, these are the things that I have solved, and would you please check? I'll definitely do it. Okay. So this is my duty.
चल जा
But again, I do not want to be like a policeman, getting all those, accounting on your submissions and okay. Can you please come back again? Yes.
Let me know which book we should refer.
See, you look at the I have uploaded the syllabus. Okay. So, there are a number of books written on the syllabus page. You can put out any of these books and try to read. But as I said, you are in an MTech class, and it's called a book or textbook in an MTech class. Try to follow what I am teaching, but I always expect you that you will read more than what I teach. In MTech classes, normally the duty of a teacher is to kind of invoke your interest on this subject and touch upon base the points that should be known by a student. But again, there is no restriction of what you can read and what knowledge you can gather. So there is a difference between an EBG course and an PG course. Is that PG course there is the horizon is very wide. So, straightforward answer to your question is that no book, no textbook, but of course refer to books. Follow the class and class notes and solve those tutorials that will help to shape up things. If you want to know much more than what I have delivered, then of course you have to go to all those different books and make yourself know. Okay.
Right.
Any other question for me? All right. So we'll see you on Wednesday. Until then, bye bye.